Hey everyone, today we are deep diving into incredibly crucial and often misunderstood concept in large-scale data processing with Apache Spark, that is bucketing. This technique is vital for optimizing the query performance on massive dataset. Starting with what is bucketing? Bucketing is the data optimization technique used in the distributed data system like Spark, Hive, and data warehouses. Its primary function is to co-locate related data into fixed predefined number of physical data files, which we call buckets. So, bucketing is a form of data clustering where rows are distributed across the fixed and user specified number of buckets or a physical file based on the hash value of one or more specified columns, known as bucketing columns. The assignment of a row to bucket is often calculated as bucket IT equal to hash column value modulo number of buckets. So, bucketing technique is designed to minimize or eliminate the expensive data shuffle operation which is typically required for joins and aggregation. Next, let's discuss the difference between partitioning and bucketing. Bucketing and partitioning are complementary data organization methods, often confused but serving different primary optimization roles. So, in partitioning, data is split into folders as per column value. For example, if we partition on column department ID and if there are 100 unique departments, 100 unique folders will be created in the output and it's useful for filtering the queries. But high cardinality column lead to too many small files, whereas in bucketing, data is split into a fixed number of files using a hash column modulo number of buckets formula. Example, if we bucket on column department ID into 4 buckets, always 4 files are created in output and it's useful for joins and aggregation. So partitioning optimizes the filtering and bucketing optimizes the join and aggregation. So let's discuss how bucketing works. The precise and deterministic mechanism of bucketing relies on the hashing algorithm used by Spark and modulo operation. Fixed bucket count denotes the total number of buckets. This value will determine the number of physical files created. Spark applies a deterministic hashing function like murmur hash 3 to the values in the designated bucketing columns. Crucially, the same input value always produces the same hash value. Then the resulting hash value is then subjected to a modulo operator with the total number of buckets. Because this process is entirely deterministic if two separate tables are bucketed on the same key with the same bucket count. For example, a record with department ID equal to 50 from the A table will always land in the same physical bucket file, example bucket 0, as the matching record for department ID equal to 50 from the table B. This guaranteed co-location is what eliminates the need for shuffling the data during the join. So the selection process for these parameters is the most critical decision when implementing the bucketing concept. Starting with the bucket count. The bucket count must strike a balance. Too low bucket count results in the large bucket files, limiting the parallelism, potentially causing the memory issue on a single executor and creating the data skew. Too high bucket count creates a massive number of small files, leading to high overhead in the file system. So the practical guide is the bucket count should be typically a multiple of total number of cores used by the cluster executor to maximize the processing, or aim for a target bucket file size that may range from 256 MB to 1 GB. To calculate the approx bucket count, divide the total data file size divide by target bucket size. For joins, both tables must use the same bucket count for the bucket optimization to engage. Next is bucketing columns. The bucketing column should be the most frequent join key or the column used most often in group by or distinct operation. For maximum benefit, two tables being joined must be bucketed on the same join keys. If this condition is met, Spark avoids the costly exchange, allowing the join to be performed by simply pairing the corresponding bucket files. Example, bucket 0 of table A joins only with the bucket 0 of the table B. So now let's discuss how bucketing physically organizes the data files. When a data frame is written using the bucket by command, the data is written to a designated table directory. Inside this directory, Spark generates exactly n physical data files. If we choose 4 buckets, we will see files namely part 0, part 1, part 2, part 3. Each file contains only the rows whose bucketing key hash to a specific index. The Hive metastore registers the structure location, storing the bucketing column name, sort column name, and the bucket count. The Spark Catalyst Optimizer reads this metadata and uses it to choose an optimal shuffle-free execution plan when possible. So bucketing is configured when saving the data to a persistent table using the data frame writer, where num buckets denotes the fixed number of physical data files to be created. This is used in the modulo operation. Calls is the bucketing column. The hash is calculated over the values in these columns. Save as table and passing the table name registers the table in the Hive metastore. Combining bucket by with sort by is the gold standard for join optimization, resulting in the most efficient form of sort merge join, such that bucketing ensure all rows with the same key are in the same physical file, whereas sorting ensure all rows within the same physical file are sorted by the key. Now let's set up our Spark environment. We are creating two data frames, df employee and df department, based on which we will demonstrate the performance difference when joining on department ID column. Here we are disabling the auto broadcast to force sort merge join for clear demonstration. If enabled, Spark may use its intelligence to use the faster broadcast join, so we are disabling it. Next, we perform the standard inner join on the raw non-bucketed data frame. The join key is department ID, and let's examine the physical plan to establish the baseline. Look at the lines starting with exchange hash partitioning. So Spark is performing a sort merge join. For this to work, it must ensure that all the rows with the same department ID are on the same worker node. This is achieved by the exchange operation, which is a massive network intensive data shuffle across the cluster. It is followed by a sort operation to prepare the data for merge phase. This shuffle and sort is the most expensive part of the join. Next, we process the DF employee data, applying the bucketing and sorting strategy to create the Hive table. We have choose four buckets, assuming a small dataset. Rows inside the each bucket are sorted by the column department ID. So Spark physically creates four Parquet files per table. Next, we read the newly bucketed table into the data frame df employee bucketed. Next, we print the metadata of the table. The describe formatted output confirms the table structure that the bucket column is department ID, sort column is again department ID, number of buckets created is 4. This metadata is now permanently associated with the table, informing the Catalyst optimizer how the data is physically laid out. Next, we apply the same bucketing strategy to the DF department table. Now, both tables, employee and department, are now bucketed on the same column, that is department ID, and sorted internally with the same bucket count 4. This is the prerequisite for the performance optimization. Next, we join the two newly bucketed tables and let's examine the physical plan to observe the optimization. So now you can see the shuffle exchange is gone. The costly exchange hash partitioning step is absent in the physical plan. Spark recognizes the table that they are pre-bucketed on the join key, allowing it to perform the join by pairing the bucket files. For example, bucket 0 from employee bucketed joins with the bucket 0 from the department bucketed, and bucket 1 from employee bucketed joins with the bucket 1 from department bucketed, etc. locally in each worker. The remaining sorting step is either a local minimal sort or logical indication that the data is treated as pre-sorted thanks to the sort by operation during the write phase. The file scan operator confirm the usage of the optimization with bucketed equal to true and the selected bucket count equal to 4 out of 4. Now, let's examine the impact of bucketing on a non-join operation, that is aggregation. Grouping by department ID on the raw department data. If we look at the physical plan, aggregation requires all the records with the same grouping key, that is department ID, be processed together for the final calculation. Since the raw data is not co-located, Spark is forced to perform an exchange hash partitioning to move all the keys to the same machine before the final hash aggregate can be computed. Next, we perform the same aggregation on the bucketed department table. So, in the output, we can see no exchange. The exchange hash partitioning step is successfully eliminated because the data is already physical grouped, or you can say co-located by department ID across the four bucket files. Spark knows that partial count and the final count can be performed entirely on the data already present on the local node or executor without the cross-network communication that is shuffle. This makes aggregation on bucketed data significantly more efficient than on non-bucketed data, further demonstrating the wide-ranging performance benefit of proper data organization. So, to wrap up, bucketing is a powerful yet often overlooked optimization strategy in Spark. By intelligently clustering the data based upon the join or grouping key, we can eliminate the need of expensive data shuffling during the crucial operation like joins and aggregation, leading to dramatically faster query times